I'll talk today about in-place processing, and the messages that we got today from Honor and others about moving data. The main message is how to save energy in general. We tried several ways to go and reduce energy by doing all kind of reduction in data movement. But what we saw in current system, that due to the new application, which is big data, in many, many cases, we have a huge bottleneck in our current system. And because of that, by eliminating these bottlenecks, we'll be able to improve performance dramatically for some cases, and by that really reduce energy in the order of magnitude almost. So we'll show here some research we are doing that related to that. So first of all, I'm just adding one foil that I got from Gary Singer from Intel, talking about the explosion of data, and all of us know about it. We see a lot of information about the exploding of data, and the basic idea of the new data environment is that everything is changing, and probably architecture will have to change according to the new applications. So we'll talk about the big data environment and the basic idea that our current system is not efficient, was not efficient built for big data, and we'll show some cases. And we have actually to go and approach our system in a heterogeneous way. So one dimension that we are talking about is the application-dependent behavior. If we look at the x-axis is the application behavior, and y can be performance and can be energy saving and so on, that definitely we know that the applications are so diverse, and the usage of data there is so diverse that definitely we can build accelerators. An accelerator means something that accelerates performance or reduce energy, and it can be an element, and the other question is where this element should be, and by that we can get much better performance, energy saving, and so on. So this is one dimension of reduction or improving in performance, and the other is time dependent. We can see that many applications along the time, and we'll see it later in some of our results, that along the time there is a different behavior along the time, and there are portions of the time that a system or the application require just much different performance or much different usage of execution. So here an example, these are 15 seconds, so this part is probably about 20 seconds, in which the system or the application ask for total different computing, and we'll see how we try to resolve that. So the outline of the talk, we talk a little bit about the trend, and then our message here is we try in this research to build a tool that its main purpose is to tell us where, when, and how should we process data. And the main question is where, and we will talk about, shall we continue to process data at the general purpose, or should we process data in storage, and we'll see why we choose the storage instead of memory to compute the data. So one thing that we realize when we have a huge data is that you cannot go and repeat visiting the same data again and again when you have petabytes of data. So we saw that the algorithm and the concept of big data is first of all skim through the data, do some computing, some filtering, and then probably do the processing itself. So there is a lot, if we are looking here, the example of the measurement we did, this is for grep on GNU. This is the time. What we did, we sampled about 10 million instructions, and we choose unique addresses. We look at the unique addresses to memory, and we counted how many times we repeat accessing the same unique address. So in the case of grep, what we can see, there is a lot of times, or most of the time, we access the data only once. In grep, of course, we compare, we read the data once, the huge amount of data, and actually the rest of the data is being read but a few times and doesn't require a lot of bandwidth when we are looking at access to the main storage. By the way, in grep, it's even more, you can see that the red one is the memory system reads, and the blue one is the memory access. So first of all, we bring from storage and we read from memory. In the case of some algorithm of grep, you bring more data that actually you read later, right? But we won't get into these details. So definitely, there's a lot, when we talk about big data introduced to us the concept of read once, non-temporal locality memory access, and that's mean something about the bandwidth that we need to access storage. So the main question that we are asking is when shall we process the data, or if we need the process of data at the storage? Let's say this is the storage, and let's say that we have some processing element, the PIS, in the storage, and we have the host processor that we use to use as for today. And the question is, first of all, when should we process at the top here, at the storage, and when we should just keep our computing at the host? And it definitely depends on the program, and what we are talking is, first of all, we like to ask what are the program parameters and the system parameter that will drive us towards computing in storage. What we did, we used an analytical model to check the viability of the concept, and then we validated via real system. So we'll see what we did. So first of all, the analytical model, and we said, actually, first of all, the program-based elements or parameters. First of all, the data intensity, which is, in a sense, the software efficiency base. Right? And we are talking about the data intensity is the byte, the access to byte per instruction. So it's the average access to memory, or bytes per memory, and really it is dependent on the software efficiency. It depends on the ISA, depends on the compiler, and so on. So if you look and you said, okay, in my program, on average, I get, 1 or 2 bytes per instruction that we have. The other is the locality factor. The locality factor is an element which is more algorithmic or application-based. And this is how much I get to memory and how much time I repeat the data to memory. And we characterize it by the alpha, which is the byte to storage per instruction versus byte to memory. And that means that, how many we have read once. If we have read once, the byte to storage per instruction is equal to byte memory per instruction. And that means that alpha will be 1 in case of read once. And this is actually, the alpha tell us what is the mixture between read once and read many that we have in the system, in the program. And then there are system-based parameters like the IPC of the processor, the number of core, the bandwidth to storage, and the frequency of operation. So let's look about the analytical model now. In this case, we have the host, access to storage, and the equation, which is pretty simple, is talking about the instruction per second, and it really depends on number of cores, frequency, and so on. When we talk about process in storage, we have very similar equation, but in this case, all the elements are elements of the storage, and we have altogether here the factor, the locality factor exists here, and if we look at the result, or before we look at the result, the main problem on this element in which we are processing in the host is actually the bandwidth limitation. And we'll see what is the bandwidth limitation and the bandwidth requirement from programs that actually are big data programs. So what we did, we decided to look, first of all, this analytical model. So we are using this equation, and we start to draw the bandwidth to storage versus the byte per instruction of the program, which is, we said, it's efficiency of the program itself, and the alpha, which alpha is actually the locality of the data, meaning how many read-once you have out of all the memory accesses. We put it in logarithmic scale, and as we can see, that the minute that alpha is reaching 1, that means that we access a lot. All our accesses are accesses to storage, and the minute the byte per instruction is high, we see here a bandwidth, a required bandwidth, very high one. And since we have bandwidth limitation access to storage, we actually will have what will happen in real life is that the bandwidth will be cut in such a way that you can't use the storage more on that. And then the question is, on the performance side, what is the implication? So definitely in the minute we access or we need bandwidth more than exist, we will see a dip in the performance. So now we have the performance on the vertical side, we have the byte per instruction, we have the alpha, which means how many read-once we have. In this case, it's 100%. So we have a huge dip in performance. And as we can see, the ratio between the plateau here, that everything is fine, and we didn't reach the memory bandwidth or the storage bandwidth, then we have this dip that will go down almost order or more than order of magnitude. So that was very nice graphs, and we said, okay, let's see if these graphs are in real life, and we can repeat it. So what we did, first of all, is we like to validate the analytical model, and then we'll see what are the limitations. So the student, Gil Shomron, said, okay, let's do it. We'll write a program in which the program behave in a different byte per instruction, it's a synthetic program, and with a different alpha, which means how many read-once we have, and then we'll measure the performance on real system. So each one of these points are points of performance that we'll measure in real system, and strangely enough, we look that, the graphs looks very, very similar. At that point, I said, hey, wait a minute, The equation is so rough and doesn't take into account so many things like the operating system, paging system, and so on. And I said, something is wrong. How can you get something so similar on a real system? And then we realized, actually, that the drop that you can see here is a drop of order of magnitude. So plus minus 30% here, so, 40% there, for operating system overhead is nothing. So really the dip here is so huge because of the bandwidth limitation that all the rest is less important in this case. So what we said, if we'll go and actually perform the processing at the storage, then we don't have the issue of bandwidth that we see here. And then, once again, we emulate the performance of an element or number of cores that actually are processing in storage. In this case, we just reduce the bandwidth limitation or eliminate the bandwidth limitation to programs, and we saw that actually what we are getting is, as we expected, this performance which is not limited by the bandwidth to storage because we are processing at a storage level. So in a sense, what we are saying, we're saying, there are programs that actually it's better to run them on the host, whenever the alpha is small and whenever the byte per instruction is small. Definitely the best performance you will get when you run on the host that was tuned for this kind of application. But the minute you're running with programs that have high alpha, which is close to 1, and high byte per instruction, you have a chance to fall into this dip that is being caused by the bandwidth to storage. And then definitely it will be much better to do the processing at the storage. We also did, at this point, we did only the analytical model of the energy saving. And the energy saving, most of the energy saving that comes here is caused not by data movement, by enabling faster performance, meaning reduce the time of execution in more or less the same power. So as you can see, the minute on current system, the minute you hit the bandwidth limit, definitely we understand that it will drop in performance, increase in runtime, and that means that the energy per instruction is going out of the roof. And definitely when you go to processing storage, in this case, you gain quite a lot because the bandwidth limitation doesn't impact when you are in storage. So let's say, and then after we saw that, I said, great, let's see if the real program behaved that way. And what we did, we took a slew of programs and we measured actually the alpha, which means how many reads ones are there in those programs and out of the old reads that exist. So, by the way, the strange thing was that, on word count, definitely there are a lot of read ones. And we'll see in a minute our surprise about these results, and grabs and so on. And there are some programs that have less read ones. On the other side, when you look at the byte per instruction, there are some programs that the required access to memory versus all the instruction is not that high. By the way, the word count surprisingly have a low byte per instruction because there are a lot of instructions that are running there in order to increase the counters and accessing byte per byte. And there are, in the grep, for example, the byte per instruction was very high. And then, as I'm saying, look at that, the alpha here, which is, there are some programs that doesn't have that alpha so high, which is algorithm-based, and the software efficiency-based, we can see a variety of byte per instruction. Another thing that we look at the time behavior of this alpha and the byte per instruction, and what we can see that in one example, we are talking about alpha, which is 1 for a long time, and then it drops to something like half, meaning there are more access, repeated access to memory versus to storage. And the byte per instruction jumps, 2x or so for a period of time and then drop back. So that's interesting. And by the way, one of the things that you realize, and we talked about it before, this period is about 20 or so seconds. So if there are portion of the programs that reaches the maximum bandwidth to storage, definitely you can run them in storage and then come back. So the basic idea, not necessarily you have to run the full application in the storage or in the host, but you can switch between them. So here what we did, we look at a contour plots, of the performance. So these are lines with the constant performance. And the dotted line represent the edge of the fall into the deep of the performance. And these elements are actually, or these results are the results of the real program that runs. So for example, if you look at grep, definitely grep uses a lot of bandwidth, and definitely process in storage can help dramatically. If you look at PSQL, right, or TPC-HQ1, it's on the edge, and probably you should program or you should run it at the host. And again, LZ, LMPLZ4, it's in the deep, but for example, the BLTN, which is a DNA sequencing, is suffering, but not too much, and probably you should run this program at the host level. This is the speed up measurements that we did for this range of application. This is a real one. We run it on a real system. We emulate the process in storage by actually running it in a smaller processor, meaning on half frequency, processor that run half frequency, and we kept the bandwidths very high by keeping the information in memory. So as you can see that in this case, for example, the speed up of 16 cores processed in host at 2.4 gigahertz versus 16 core in the process in storage at 1.2, meaning in a half of the performance. And what we can see that there are some cases in which we are getting 2x in performance, some cases we get more than 3x, and some cases that it doesn't make sense at all to run it in storage. And definitely the more programs that are a big database, the better for them is to run on the storage. Okay, conclusion. The basic idea that we are talking is that the process in place, and in this case in storage, is really depends on the program that you're running. And for that, we built kind of a tool that actually will run the program and will tell us if the BMPI and the alpha, what is the level of BMPI and alpha. And by knowing the system parameters, the bandwidth, the IPC of the processors, the number of cores and so on, we'll be able to predict that running this specific program will be over the bandwidth to storage or below the bandwidth to storage, and by that recommend to run this program or in storage or at the host. By the way, we believe that by having this kind of system in which you have processing in host and processing storage, that we are not the first one to talk about it, but we are talking about which program it's better to run in the host or in storage. But definitely the minute we'll have this element, two computing element, one close to storage and one close to the main host, some communication between these two can enable you to achieve much better overall performance reduction in energy in the system. Thank you.